Okay, let's get started. So I hope you guys had some good time in the exercises in the labs. Can you hear me well in the back? I think. Okay. So yeah, the lab this week was on optimization, right? To really implement gradient descent, and also there was a second part on the subgradients. So that one we are actually going to discuss now again. So if you were confused about the mean absolute error, how to compute the gradient of that, I'm going to explain that in a minute. Yeah. But yeah, the lab we have now, which is the first real programming lab, it's really important for you to see both the practical aspect of how to train a machine learning model, but also the theoretical aspect on how to compute the gradient, what even is it, what can go wrong, right? Maybe you got the minus sign wrong and you can see what happens, plot where the point is going to go, and how really observe how gradient descent works, how the training works, and even the simpler grid search. Yeah. So yeah, it takes a bit of time, this lab, but it's an important one for the course. I want to just briefly recap again what we've done last Tuesday. So just to clarify again a bit more, what is a gradient and what does it mean to take this gradient step to optimize. So this is the picture we showed in like d+1 dimensions, right? So the parameters we optimize are a variable that lives in 2 dimensions on the bottom, and then the vertical one is how big is my function value. So then the gradient, it can be seen as a kind of a plane, which is the tangent to the graph. So it's the vector which actually describes this plane. It's the normal vector, so to say, of this plane, but it's only in the 2 dimensions. The gradient lives in 2 dimensions. So that might be a bit confusing. So I'll give you also another interpretation, which is much easier to plot, also, which is just to look at the ground plane. It's just these 2 variables, W0 and W1. So then the picture looks a bit like a map and a landscape. You know, you have the altitude and stuff, so you can plot the altitude lines if you want. So this is the top of or the bottom of my mountain. So here is the line where the function is value, I don't know, 1. Then here is another line. So these are the lines where we have the same altitude, where the function value is the same. So I can plot this kind of picture here. Maybe it's 2, 3, 4, and so on. So there the function gets higher and higher. So we want to plot the thing we have on the left. So it has a minimum in the middle, and then it gets higher. So this is the line with value 2, 3, 4, 5, and so. Okay, what we want to do is we want to get to the optimum, which is here. But where we actually are is, let's say, here. That's our current iterate, as we call it, the current point, Wt, right? So now, what does a gradient step do? It's a step which is actually orthogonal to this line of same height, of same function value. So the gradient is going to point kind of orthogonal to where it's flat, right? It's pointing into the direction where it's going down the most rapidly. So this one would actually be orthogonal if you want to interpret it, but it's not even necessary to think too much about the geometry, but it's better to think about it in the algebraic sense as we defined it. It's the change rate in each of the coordinates. So this is the negative gradient of the L function. And so that's going to bring us to our next point, maybe with a step size, right? So we are going to go there, then the next step will bring us here, and it's going to maybe get closer to the optimum if you pick the right step size. Just to clarify again, this is the picture in 2 dimensions corresponding to the picture we had on the left in 3 dimensions. And that's also what you implemented today in the lab. Yeah. Okay. Yeah, there's any comments on this? Okay, then, so what we did on Tuesday was up to gradient descent. So how does it actually work, and see a concrete example with this 1 dimension. So you can have a step size too small, or you can have a step size too large. So we said if it's between 0 and 2, it's fine. And if you pick a negative step size, actually, then it would also have a divergence. So it would go away from where we want to go. So I'll come back to that. Yeah. So this was to say that in this example, things do converge, right? By the way, I'll upload the notes later today. Yeah. So the annotated ones. Okay. How you compute it, how you compute the gradients, that's mostly for your lab to really compute this derivative, use the chain rule. And again, there are 2 ways to do it. Either you do it for each variable separately. I do it for my value W7. I compute the derivative to that variable, all separately, and then put them all into a large vector. And then you're going to realize, in some cases, we'll have a rather easy form. So we have seen stochastic gradient, which is when the function we optimize has an additional property, and that property is that the function is a sum of some other functions. So that's what we had here, right? Okay, that's stochastic gradient descent, and we said that yes, it has a nice property that actually the property that makes it work is the following, that if you just take the gradient with respect to one of these functions, you get something. It depends on which point you actually picked, which n you picked. But the nice thing is that this thing, we call it the G vector, which is the same thing as we then use in the step. That thing happens to have the right expectation, right? Because in expectation over these n points you pick, that's expectation actually is this average here, if you want to compute it. Turns out that is exactly the gradient of the original function we want to optimize, which is a very nice coincidence. So it's this true gradient in expectation, and that's why this method kind of works. Yeah. And that's again why it's called unbiased. Okay, so there is, this might be, if you're not familiar with expectation, then you might want to revisit the definition of that, but it's very simple. Here we just use it for a discrete random outcome that we pick a number from 1 to n randomly, uniformly, and then we look at one entry of the gradient, see what that number does, but on average it has the right value, right? Okay, here's a variant. So far we said we only pick one data point, that means one of the Ln functions. But what we're going to do now is we want to interpolate a bit between stochastic gradient, which picks only one point, and the classical gradient we've seen before, where we use the full gradient of the full objective L. Is there something in between? And yes, there is, and that's called a mini-batch stochastic gradient. So here is that algorithm. It looks a bit like the old gradient descent. So first, imagine that you would do this sum here. So these are the n's that I pick. So for example, you could pick all the data examples. So this set B is a set of points, right? So I can pick all the data points if I want. This set from 1 to n, right? That's all the L functions I have. And what it then does, it's just building the average over the ones I have chosen to be in my set. So now that's one step of it. And that turns out that this is plain old gradient descent as we have seen it before. So some people call this full gradient descent or batch gradient descent. So we are back to the old method. So the interesting bit happens if you don't pick all but only a few. So the other extreme is when you only pick one of them, right? If you let B only be one of the random data points, then we get stochastic gradient descent, right? So one of the n's we picked, and we only use that n function, and the others we don't use. So that's the two extremes. And in this middle ground, when we just use a few, let's say 5 data examples and so on, then we have a mini batch. So we use 5 examples, 5 data points, compute their gradients, average them, and that is going to be the direction in which we move. So why would anyone want to do this? So here's one example. Then you get SGD, right? So why would you pick a set of, let's say, 5 points? Anyone has any idea why this could be a good idea to do? Oh. Yeah.
Increase performance, but actually decrease the probability of error or increase the probability of. So increasing performance versus.
Why would you say it increases performance? So.
Well, in comparison to only one selection of.
Yeah, you're right. Yeah, compared to only one, this means we use more information. It's a more stable information, right? So if you use all of them, you would have perfect information. We get. Yeah. Yeah, exactly. It's some kind of middle ground. Yeah. So if you have it very large, then you get the gradient descent back, which is very stable, but also expensive, right? But the fun thing is that another aspect of performance, as you mentioned, is that once you have said that I want to pick 5 of them, I can actually compute them in parallel, right? So maybe I have some device, or maybe I have 5 computers or so. Then each of them can do the job of just computing the gradient of one of these ln functions, right? So that can be parallelized. Because you see it here, we are currently at the step WT, that's our position, right? And we have to compute now not only one gradient, that's what we had previously in SGD, stochastic gradient, but now we have to compute 5 of them to form our step, right? But this is taking a lot of time. That's the important computation. In a neural network, you would need to feed the whole example into it, compute the gradient, do this flow through the network. Don't worry, this is going to come later, but I'm just saying computing these gradients takes time. You also see it in the linear regression today in the lab. You saw that that's where all the computation is spent. So if we can parallelize it, then that's a nice property. And so yeah, that's one good property of using a mini batch, and that's exactly how all practical machine learning systems do the parallelization. So I mean, we're not getting into technical details here. Like a graphic card, that's exactly a device like that. So I'm not a hardware expert, but they just do the same operation. They can, I don't know, add 2 numbers, but they can do it 200 times, right? At the same time as you do it on a regular processor. So what they can do is they can compute 200 of these gradients at the same time as you can compute 1 with a regular computer. So that's why this could be a nice idea if you say my mini batch is, let's say, 200 or just as many compute agents as I have available to then get a more stable step. And you can also try this out in the exercise. You will see a bit if the mini batch is very small, just 1, then it will jump around quite a lot. There's a lot of noise, but it's it's cheap, right? And if the mini batch becomes very big, then it becomes more stable, but there's more overall computation to do to then have one step actually happening. Yeah, and that's what the lab is about, that you already started working on today. So yeah, have gradient descent for the linear regression with mean square. And now we also have this SGD, which is much cheaper. So it's actually n times cheaper to do such a step with a batch size 1 than it is to do a full gradient step. Let's summarize this again a bit to be clear about how expensive is it to compute it then. So maybe we finished this last Tuesday, was a bit at the end. So let's again be precise. How do I compute the gradient and how do I compute the stochastic gradient? Okay. So, I mean, this is also in the lab, giving away the solutions. So for gradient descent, right, I'll do it for linear regression. So what we want to optimize is the full L function, and it was defined as the average of all the costs of each data point. And yeah, what was that? So I do 1/2, it doesn't matter. So the cost was the target minus the prediction. So what's the prediction we do? It's the data times W. And that's squared, so that's mean squared error for linear regression. Okay, so what's the gradient of that? That, again, as we said, there are two ways to do it. Either you know what the gradient with respect to a vector variable is, or you just compute it separately for each entry of W. I'm going to take a shortcut here, actually. I'm going to do it, but I will see that it's actually much easier to compute the gradient for SGD. That's because I will only need one data point. So this we'll do in a minute, but let's do it for just one data point. That's much easier. So the function ln, so which our entire function is the average of, what is that? Well, it's just this part. That's ln, actually with a 1/2. Yeah. So. Okay, that's the contribution of the nth data point to the error, right? Xn is the vector and W is the vector. We multiply them together, we get a number. So it's very easy to compute the gradient of that one. So I guess you already did this. I hope I'm not boring you too much. So it's the what's in the bracket, right? Because it's squared. So this number, then, and this number is multiplied by the inner derivative. So what's the inner derivative? So because now it's a derivative with respect to a vector. But let's do it individually. The inner derivative with respect to W7, or just one entry of W. That inner derivative is, yeah, can somebody tell me? Derivative with respect to W7. What is that? Exactly. Here the answer is minus xn7. So that should be the seventh entry of the gradient, right? So if that's what we compute, right, then that's the answer. So we're not interested only in the seventh of these entries, but we are interested in all of them, and there are actually d many. So the whole thing will just be stacking all these numbers x and d into one very long vector, and that is the resulting gradient. It's a vector in d dimensions. Sorry, I'm writing very ugly. But what happens is if I stack them all together, not only the seventh one, that means I'm going to use all the entries of x. So then I can actually just keep x as a vector. That's the little trick here. This is a vector, right? And this is also a vector. They live in d dimensions. Okay, that's just to clarify that. So now I have this vector, which is the gradient of the nth data point. Now I can use that to get the gradient of the whole objective if I would want to do something here. And that's very easy because sums of gradients are just gradients of sums and the other way around. So it's not hard to verify that that thing is actually the sum of what we have here. And that sum, if you want, you can write it simply as the X matrix times this thing here. That's just a trick to write the sum, but of course you can also do it manually. And the 1 over n stays here. Yeah. And I forgot a minus, of course, because here there is a minus, and also here there will be a minus from the inner derivative. Okay, that's all nice. But what's the point? The point is that this one here costs n times d to compute, and the one on the bottom is only costing you d to compute. So maybe some of you are not familiar with this O notation. It just means that the order of magnitude, when these two numbers become very, very large, then the order of magnitude is this, right? If n and d are 1,000,000, then the order of it is what we write like this. So you can actually check it in the appendix. There's a definition if you're not familiar with that. It just means that we don't care if it's 7 times n times d, but we just say it's n times d in the order. So that is a huge difference. A step from the stochastic method on the bottom is n times cheaper than a step of the full method. And that's why it's such a popular method in all of machine learning applications. Okay, there is one thing in between. So yeah, how expensive is actually this mini batch stuff when we don't do it for one extreme point as here, but if we do it for a set B, let's say 5 of the points, then can you tell me how much I then have to spend to compute one step? So
B, if like the cardinality of B is a constant, it's small as well. Otherwise, it's like cardinality of B multiplied by B.
Yeah, so you're right. In the mini batch, you say that the complexity is basically size of the mini batch times d. Yeah. Size of the mini batch that we wrote like that, and then d is what it costs me to get one of these guys, right? So that's why the mini batch variant takes this much time for one iteration. So okay, that's already the main thing we need to know. And are there any questions on this?
Why do you have cardinality of B?
Why do I have cardinality of B here? So this is just for this special variant for mini batch SGD. So mini batch means I pick not only one guy, but I pick B of them, right? So that, and I build the average of them. Sorry, yeah, B, I here wrote it as a set, but yeah, it can also be a number, yeah. So, yeah, sorry, B, you can write it as a set, yeah. Okay, other questions? I make a little bracket here, not too confusing. Okay, so that's all we need to optimize functions which we can differentiate. So And now, today in the lab, there was actually this one function which was a bit more annoying because it was the absolute error. And that one, you know, it looked a bit like that. So here it's just linear, but at 0 there is a bit of a problem, right? It was not differentiable. So now we want to say a few words when we optimize something and that something is not differentiable. So you can call this non-smooth as well, yeah. So okay, to get there, what we want to do is we want to define a generalization of a gradient, which is actually called a subgradient. So which is something slightly more general than that. And before we can do that, we want to revise again what it means to be convex. And here is a very nice property that convex functions have, is namely that if a function is convex, then it's lying above its tangent plane, which is the linearization. So maybe for those of you who were a bit puzzled by the tangent plane I had on Tuesday or also at the beginning today, here I'm going to clarify this now. Here it's much easier because here is actually what this tangent plane precisely is. We will define it here. So again, I'll just plot the function value against the parameter. Okay, what is this plane, this crazy tangent plane? We are here. So the green function is a tangent plane, and it's defined like this. So we are currently at W. That's this base point here. And what we do is we just look at the linearization of our function at that point. And here is how it's defined. You just take the gradient, and then you get, if you want to know how this thing is at the point U, then here is the formula. So this is U. So that, for those of you who know the Taylor expansion, that's exactly the first order Taylor expansion of the function. That's fine, and the point is that if a function is convex, then it lies above that. So the above is here, means that the true function, the red one, is actually above the green one, right? That's nice, but now what if we don't have the gradient? If it's not completely differentiable, if this thing here is a problem, this vector, then we can still define a subgradient. And what it is it's a vector like the one we had here before, but just defined differently, but also having the same property. It's defined by just having this property, the property that the function is actually above it. So you can use any vector you like, vector g, and you can ask, does my function lie above the linearization defined by this g? So that's the idea. But let's illustrate it in a picture. It's much easier. So this picture is always tricky to draw. Not so far, but so let's consider a function. And it's kind of round. So this is a convex function, right? And this is all nicely differentiable. If I'm like here, I can easily compute the derivative for the gradient. Things are fine. There is one tangent plane. But there is a point here, and here things are a bit strange. So at this point, it seems that there are several possible tangent planes. So yeah, this is one, and some more. So this is defined by some vector g. This is another one, g prime, whatever. So there are many of these planes, and here is how each of the planes is defined, same way as we had above. You can use any vector g, you get a plane like that. And now if it happens that the true functional is above it, then we say that g is a subgradient to our function. That's the definition. So. Okay, so now maybe you're at some point, maybe you cannot find the gradient, you don't know how to compute the derivative, but maybe you can find such a g. So there's several to choose from maybe, we don't need all of them, but we want to work with one of them. We want to find one g vector which defines such a green plane such that it's actually below our function at our current position. And then what we're going to do later is we're going to use this vector instead of the gradient vector. So that's the idea of subgradients. There is this, why is this, what does this have to do with the old thing? So it's actually a generalization, right? So because if you're at one of the regular, the boring normal points here, then there is actually there is only one supporting tangent. I mentioned this before. So here there is only one plane. And if there is only one subgradient, then that thing will actually coincide with the gradient. So if your function happens to be differentiable where you are, then fine, then the only thing which satisfies this condition is actually the gradient itself. That's why they're basically the same thing, but the subgradient generalizes the old definition. Okay, so maybe it's best to play around with this as an example, yeah, or question.
Can you just go a little bit outside? Okay. So for concave functions, we don't have gradients.
Yeah, what's the role of convexity here? So it's funny. So far, the subgradient you can define anyway. The definition is there for any function. But now you can ask, yeah, when do these things actually exist? And you asked about, so what if my function is like that? That's what we call concave. And then, yeah, this is pretty bad. So you're right. In this one, then there exists no subgradient. So yeah. That's yeah, it's good to keep in mind. Let's keep this example when it's like that. Then yeah, bad luck. So it's differentiable, but unfortunately it's not a subgradient. So this thing is not satisfying our property. Actually, it turns out the fact that your function does have subgradients, that actually turns out to be equivalent to being convex. But we don't need this precise theorem here. So, but if you're interested, you can read or you can prove that this is the case. Yeah. Okay, let's do an example. Then it's maybe more helpful. So this is just the definition so far. Yeah. Okay, let's use it to do something useful, and that's when we use it to optimize. So now we all know gradient descent already, but now we can use these vectors instead. So now we can optimize a bit of a larger class of L functions, even if they're not completely differentiable, right? So, and yeah, that's all it is. So here again, I'm just going to use I'm somewhere at W, and I will want to find a vector which is a subgradient at where I am. And if I find such a vector, then I will use it to perform a step exactly the same way as we have seen, so just as with gradients descent. Okay, and then that's the algorithm, same as we had before, right? And now let's apply it, and that's exactly the second part of the lab this week, which is for absolute error, which is exactly what we wondered before, right? What if my function looks like that? Then it's not differentiable at the point 0, and at the other points it is. Okay, yeah, can anybody tell me? So depending, okay, let's call our variable e, maybe it's a bit easier. What actually is the subgradient of this thing, depending on my variable? So I'm at the point e, and I'm asking, what is a subgradient here where I am? Sometimes people write the set of subgradients like this. Yeah. Subgradient of h at my current position. So this is the set including all these guys, and here we have only one parameter. So which of these parameters is the subgradient at e? So
-1 plus 1.
okay, but for which e? So
For e equals 0.
for e is equal to 0, you are claiming that it's anything from -1 to 1. Okay, I need a bit more space here. So that's actually true. So let's find such a vector which is such a subgradient thing. Okay, what is it? This is a set, and it depends a bit on where we are. So you looked at the case when e is 0. And you said all the numbers which are actually these subgradients, they are the numbers between -1 and 1. And that's exactly the case, because here is the one if you set it to -1, here's whatever, -0.5 or something, and here is if it would be +1. So if you are at 0, then yes, then you have infinitely many choices, and all of these are fine. And if you're not at 0, then it's even easier. So if you're in the negative part, then it's actually differentiable, and this is just one choice, and that choice is the slope, right? The gradient is the slope. So the slope is -1. And if you're on the right side, then it's actually 1. Okay, that's nice, so all fine. This is for one variable. And now it gets more fun when we try to combine it. So now we put a machine learning model which does a prediction, and then that thing goes into the absolute error, like this. So then it becomes a bit more tricky. So now we actually have to use chain rule to compute a subgradient of the full objective function, right? We don't care only about this, but we want to know the dependence of our cost really on the weights w. And so yeah, this is just to mention that this is a really important class of functions. It sounds like, why would you care so much about this absolute value? But this is used a lot. We've seen it's more robust than the mean squared error, and mean squared is also used a lot for all machine learning models, whatever they are. And then there is even another function which appears a lot in machine learning, which is this function here, which is basically the activation function they use in neural nets when they do. It's called ReLU, but it doesn't matter so much. Rectified linear unit. Or it's also used in linear classifiers, where it's called the hinge loss. So it's not so important, but if you're interested, here is another function which is very simple. It's just flat on the left, and slope is 1 on the right. And that function is also appearing a lot. And for this one, we can do exactly the same as we did. We can do gradient steps on these kind of problems by what we said, right? Everything is fine everywhere, except if we are at 0, we have to be a bit careful, or actually, we even have more choices then we have to make a choice which is a subgradient. And again, here there are many, many choices, so anything like that is fine, as long as it's below the function. So, okay. Yeah, then for how to use the chain rule, this is what you're going to do in the lab. So there is actually a hint on the lab sheet on how to do that. Maybe I'll try to give it here. If you have f of w is, I don't know, g of h of w. So yeah, if h is differentiable, then yeah, then a subgradient of this thing is actually, yeah, it's just a regular chain rule. It's a subgradient of the g function. Have to be careful that I get this right. Times the gradient of the inner derivative, the inner function, the h function. Okay, and then these things here, they are meant as a, so this is a set, right? All the candidates who satisfy the property, they belong to these sets. So here the green stuff, the set of all subgradients of the whole combined function. That set, you get it when you take the set from the g function. So, well, plug in h, and then many things will be subgradients, all these guys. And each of them, if you multiply it with the inner derivative, then you get another vector. So, sorry, this may be a bit confusing, but take an element of this thing. I can call, I'm running out of variables, so an element here is an element of this set here times this vector here. So, yeah, take any element of the g subgradient, multiply it with this vector, you get an element of the subgradient of the entire combined function. Did I get this right? It's the same as on the lab. There was a different notation there, but yeah. Okay, very good to play with that and really experience it yourself. You can check it, right? How do you check if you got it right? You just check it at 2 points. Is it true that the function is actually above the linearization? If yes, you got it right, and otherwise maybe you forgot a minus sign or something. Okay, that's a generalization of gradients and of gradient descent. And obviously you can do the same with the stochastic case when our objective function has a sum again, but maybe that's still not differentiable. So in the exactly same scenario, you can, instead of using gradients for one data point, use subgradients of that data point. So it's really the exact same thing as we had for subgradient descent, for stochastic gradient descent. We can again apply it the same way. So you select one of these randomly, and you use a subgradient of that one function. So this is very useful. So yeah, now we've seen a lot of things. I will summarize it briefly. And in the lab, you will actually have all the 4 cases here. So let me try to have this little table. So we had smooth functions. That was the case for least squares. And we had non-smooth functions, which was the case for the absolute error. So these are not differentiable. That was what we tried to solve, right? The L. And the algorithms we looked at was gradient descent and stochastic gradient descent. So, you know, here we used the whole L, and here we only used the one from one data point. And yeah, this is for mean squared error. That's an example, and here mean absolute error, that's another example. And yeah, we discussed the complexities of these things. That's very important. How long does it take? And both gradient and subgradient descent, they are very slow if you compute the full function, right? D times n. And then if you only use one data point instead, you only pay the cost d for one step. And that's actually the whole picture. So this is for linear regression. So. And this is which algorithm we use here. So here, it's just about the naming. Maybe the naming is a bit confusing at first, right? So when we do gradient step, then of course we use gradients, right? And if our function happens to be in the right column where it's not differentiable, then what we do is we use the subgradient to perform our step. So okay, that's the whole picture for this first part of optimization. It's a good point to ask some questions. Or to take a break, actually, and see you again in 15 minutes.